Hi there. Let's take a look at practice problem set number 2 that I've set up for you. Okay, the first problem here, we've got two vehicles moving here. Two cars travel in the same direction along a straight highway. One at a constant speed of 55 miles per hour and the other at 70 miles per hour. So we take a look at this. We've got some givens here. So let's take a look at what we've got here that's given. First, we have the velocity of car 1 at 55 miles per hour and the velocity of the second car at 70 miles per hour. And looking at this, we set up the fact that initially we have a distance of 0 miles and a final distance of 10 miles. Okay. We have a time final with a 15-minute lead here. Okay, these are all given to us in the problem. Okay, so A says, assuming that they start at the same point, how much sooner does the faster car arrive at the destination 10 miles away? Okay, so there's our given there of 10 miles. The solution then is done by using average velocity expression. So our average velocity, v, is equal to x divided by t, which basically comes from the expression of the distance equal to velocity times time. So we've just moved the terms around. So if we move the terms around one more time and solve for t, we will have the distance divided by the velocity, the average velocity. Okay, so the average velocity is our velocity from beginning to end. Okay, so let's take a look at the time for car 1. Using the expression x divided by velocity, the average velocity, so the distance for car 1 after 10 miles at its average velocity of 55 miles per hour gives us a value of 0.182 hours, which we're going to convert then and end up with a value in minutes. Okay, so that we know there are 60 minutes in an hour, so when we multiply these through, our hours cancel in the numerator and the denominator, and we're left with a total time traveled by car 1 of 10 minutes 0.91. Okay, 10.91 minutes. Now let's do the same thing for car 2. Again, we use the same expression we used here, x divided by v. So now we've got the distance again of 10 miles that we're looking for after 10 miles and an average velocity for car 2 now of 70 miles per hour. So when we divide 70 into 10, we get 0.143 hours because the miles cancel out. And again, we're going to convert to minutes, 60 minutes per hour. So we now have, this should be car 2, not car 1. We now have car 2 at 8.57 minutes. So now if we look at the difference, that's what that delta is telling here, the delta time. The difference between the time of car 1 and the time for car 2, 10.91 minutes minus 8.57 minutes gives us a difference in time of 2.34 minutes. So it asks us to then determine how much sooner does the faster car arrive at the destination. So car 2 moving at 70 miles per hour arrives 2.34 minutes sooner. Let's move this up here. How much faster how far must the faster car travel before it has a 15-minute lead on the slower car. So what we're going to do is we're going to substitute the expression again of distance equals velocity times time to solve for distance x. We're going to solve for one in terms of the other. So in doing this, we're going to convert minutes to hours, okay, knowing that we have 15 minutes is equal to a quarter of an hour, and we run that through the relationship x equals velocity times time. We have a velocity of 55 miles per hour for the first car, and we're going to let t equal the unknown distance x in miles by the speed of the second car, 70 miles per hour, and it is a 15-minute lead, so we're going to add 0.25 hours, or that 15-minute lead. So let's take the expression here then, x is equal to velocity times time. So now we have one in terms of the other. We have a time value that we're going to insert into the expression, 55 miles per hour, then, and then all of this, x miles per hour divided by 70 miles per hour for the second car plus the 15-minute lead. So we end up with 55 over 70. Those are just numbers, so we can factor them out. Multiply that times the unknown x miles, and then we are going to add the terms when we multiply this through here, and 55 times this, 55 times a quarter, and in terms of miles now, because our hours cancel out. So the expression now simplifies to x is equal to 0.786 times x miles plus 13.75 miles. Okay, so all we've done is simplify this term and this term. Now we have terms on the left and the right side that have x in it, so why don't we combine our terms? So let's move the second term over and subtract it from x. So when we subtract 0.786 from x, we're left with just 1375 on the other side of the equation. Now we can factor our x out. When we do, we have 1 minus 0.786 is equal to 13.75. Solving now just for x, we can take all of this term, which is just a number, and move it to the other side of the equation. So in doing so, we have 1 minus 0.786 divided into 13.75, which gives us 74.17 miles. So the faster car travels about 64.2 miles before it has a 15-minute lead. Let's take a look now. Problem 2. A person takes a trip driving with a constant speed of 89.5 kilometers per hour. Except for a 22-minute rest stop, if the person's average speed is 77.8 kilometers per hour, they want us to first solve for how much time is spent on the trip. Okay, if we look at the graphical relationship here, we end up with the velocity kilometers per hour, and we end up with the time in hours. So our average velocity is 89.5 kilometers per hour. Okay, that's given to us in the problem. The average time then given in the problem is 77.8 kilometers per hour. And they're looking for then us to also take into account the 22-minute rest stop. Okay, so we can see here that we've put the 22-minute rest stop into the graph. So the total time for the trip then becomes T1 plus the amount for the rest stop. So T1, we convert that to hours. We end up with 0.367 hours when we convert minutes to hours. T1 then is the time spent traveling at the average or the constant speed of 89.5. Okay, so thus the distance traveled, going back to the relationship, distance equals velocity times time, in this case average velocity. There's our average velocity of 89.5 kilometers per hour times t1. Okay, so this gives us a value then of the average 77.8 kilometers per hour times this expression we solved for here, t1 plus 0.67 hours. Now what we're going to do in this term is we're going to start combining terms. So on this side of the relationship we have the average velocity times time, and on this side of the expression we are going to take our average velocity and then this value of 77.8, we're going to multiply it times both terms. Okay, so we've got this times t1, we've got this times this value. So you can see we have both of these terms ready to multiply through. Nothing we can do with this because we still have an unknown t1. So when we do that, we're left with our t1s on both sides, and this simplifies to 28.5 kilometers. Now we can move this term and this term to the same side, so let's move the 77.8 by subtracting it from the other side of the equation, and that just leaves us the 28.5 kilometers on this side. Now I can take t1, separate it by taking the difference in 89.5 from 77.8, I get 11.7 kilometers per hour. Divide that into the 28.5, and I have about 2.5 hours, 2.44 hours. Now I can take that value for t1, put it back into the expression up here that we solved for. Sorry about that. Yeah, it's not going to do it. Anyway, t1 plus 0.67 and 2.44 plus 3.76 gives us 2.8 hours. So that is the total time, 2.8 hours. Now knowing that, the second part of the problem asks how far does the person travel? Again, we come back to the same expression, velocity or distance equals velocity times time. 77.8 kilometers per hour was the average speed. Multiply that by 2.8 hours, we get 218 kilometers is the distance the person traveled. Okay, so if you take a look at each of the steps here, I think you'll see that it's really a solving one in terms of the other and then substituting the values when one is served and resolved. Problem 3, this is our problem where we are throwing an object straight up vertically. So we have a ball that's thrown vertically upward with a speed of 25 meters per second. Okay, this is a 4-part problem. The first part asks us how high does it rise. Second part, how long does it take to reach the highest point. The third part, how long does the ball take to hit the ground after it reaches the highest point. And then the fourth, what is the velocity when it returns to the level from which it started. So let's take a look at A. How high does it rise? So we have an initial velocity of 25 meters per second. We have a final velocity of 0 meters per second. Initial time, when we're just starting the stopwatch, is 0 seconds. So based on the values that we're given here, we can use the relationship of velocity squared final is equal to velocity initial squared minus 2 times the gravity times the change in height. Okay, so if we look at this, velocity final is equal to velocity y max, which is 0, which is telling us once it reaches the top at the maximum height, the ball actually stops, so its velocity is 0. So going back then to our expression here, velocity squared final. Let's move the velocity initial squared final to the other side of the equation, is equal to minus 2 times the gravity times the change in height. Okay, if we take all of this term then and solve it for the change in height, delta y, we end up with velocity squared final initial minus velocity squared, or velocity squared initial minus velocity squared final divided by 2g. Why did these terms change? Well, because of that negative sign. When we moved the negative sign to the other side, this became positive, this became negative. So now it's just a matter of inserting our values. The initial velocity, 25 meters squared, or 25 meters per second squared, minus the final velocity, that's at the top, is 0. 2 times gravity, 9.8 meters per second squared. Then when we square 25, we get 625 meters squared per second squared, and we divide it by 2 times 9.8, or 19.6 meters per second squared, which gives us then the height that the ball reaches of almost 32 meters, 31.9. So now we have another value that we know, that the ball reaches almost 32 meters. B part of the problem asks how long does it take to reach its highest point. So to do that, let's choose the expression velocity final is equal to velocity naught initial minus velocity time, or gravity times time. So let's move the terms around. Velocity final minus velocity initial, when we move it to the other side, is equal to minus the gravity times time. Again, if we move the negative sign, that's an understood minus 1. If we move it to the other side of the expression, you can see that what we end up with then is a negative then becoming a positive on the other side. Okay. So now we have one more step. Let's move gravity to the other side of the equation by dividing through both sides. We end up with the time is equal to velocity final plus velocity initial divided by the gravity. So velocity final, again, that's the velocity at the top, is 0. The velocity initial was the value 25 meters per second. We divide that through by gravity, 9.8 meters per second squared. We get a time now of 2.55 seconds. Part C of the problem says how long does the ball take to hit the ground after it reaches its highest point. Okay, the same amount of time, 2.55 seconds. Okay, so if we take our relationship, the distance, the change in height, delta y, is equal to velocity initial times time minus 1/2 the gravity times time squared. We're calling that velocity initial is equal to 0 at y max. Okay, so we can start plugging values in. Delta y is equal to 0 times time minus 1/2 the gravity times time squared. So since all of this term is 0, we're left with 1/2 gravity times squared. So we can move terms around. Let's take the 2 and move it to the other side of the relationship. So now we have 2 times the change in height is equal to minus the gravity times time squared. And if we solve for time squared, since we're looking for how long does it take in time, we're going to move all of these we're going to move the g to the other side of the equation and set it up so that now we're solving for time squared. So time squared is equal to minus 2 times the change in height divided by gravity. Okay, we're not looking for time squared, we're looking for time, so what we need to do is take the square root of both sides of this expression. If we take the square root of this side, we're just left with t. If we take the square root of this side, the square root in fact stays. Okay, so 2 times the change in height, well, that's what we solved for in part A, divided by gravity. Okay, so now when we just multiply these terms through, divide by gravity, again we can see that the time is 2.55 seconds. So by inspection we would have known that without going through all that math. Okay. The last part then says what is its final velocity when it returns to level from where it started. Okay, again, this is the same as the initial velocity, 25 meters per second. So if we want to prove this, we can take the velocity final minus the velocity initial minus gravity times time. Put our values in. We know that gravity initial is 0 meters per second. Gravity times the amount of time it took, 2.55, again gives us now a final velocity of minus 25 meters per second downward, hence the negative sign. Alright, problem 4. Another problem where we're tossing a ball in the air. A ball thrown vertically upward is caught by the thrower after 2 seconds. Find the initial velocity of the ball. Okay, so if we take a look at this, again, time initial 0, velocity final, we know at the top is 0 because gravity acts on it and stops the ball, and then time final, in this case, is 2 seconds. So find the initial velocity of the ball. If we use the expressions where we can look at the initial height is equal to the final height, that value is equal to 0 because that is the starting point. Again, if we look at the time initial and the time final, we end up with 0 seconds. Okay, where time initial is equal to t naught, 0 seconds. Time final, though, is 2 seconds. That's the total trip. Okay, up and down. We have the gravity then still equal to, we're going to take the gravity as downward, hence the negative sign, 9.8 meters per second squared. So if we take up as positive, for the total trip from beginning to end, the initial height is equal to the final height, in this case starting and stopping point gives us a 0. Gravity minus 9.8 meters per second squared is telling us gravity is pulling downward, and the time final is the total trip, 2 seconds. Notice that the start and end point for the trip are the same. So, by the rules, the displacement has to be 0. If we start here, go up, come back down, we've in essence gone through 0 displacement. So if we take a look at the expression, the change in height, delta y, is equal to the difference in the final height minus the initial height, and we set that equal to the initial velocity times time minus 1/2 the gravity times time squared. Again, knowing that the change in height or the displacement is 0, this whole term goes to 0. So what we're left with is the initial velocity times the round trip, 2 seconds, minus 1/2 times gravity, 9.8 meters per second squared, times 2 seconds, which is the total trip, squared. Okay, since we have a 0 on the left-hand side of the relationship, we can start moving things around. The negative sign will work itself out so that everything becomes positive. So in essence, the velocity initial times 2 seconds for the total flight now is equal to 1/2 of the gravity, 9.8 meters per second squared, times, when we square this, 4 seconds squared. So if we move the 2 seconds, multiply 2 seconds times 2, we end up with 4 seconds in the denominator, divided into 9.8 meters per second squared times 4 seconds squared. You can see that our seconds squareds are going to cancel out, and we are going to have meters per second, which is what we're looking for the velocity. So in this case, the initial velocity looks a lot like the acceleration number for gravity, 9.8 meters per second. The second part of the problem asks us to find the minimum or the maximum height that the ball reaches. So we're looking at, if we start from 0 and we go to the point where gravity stops the ball, that becomes the maximum height. So y maximum, the relationship is 1/2 the velocity initial plus the velocity times time. Okay, since we know that the initial velocity is 0, we can multiply through then 1/2 times the velocity times time. Okay, so we know the velocity is 9.8 meters per second squared, or meters per second. As we insert that value, multiply it times half the trip, which is 1 second, we end up with half of 9.8, which gives us a height of 4.9 meters. So that's the maximum height that the ball travels. The last problem, an interesting problem here, says in Bosnia, the ultimate test of a man's courage used to be jumping off a 400-year-old bridge. The bridge has now been destroyed, into the river Neretva, 23 meters below the bridge. So let's take a look at and gather everything that we can for the givens in this problem. First off, we know that the height, or the distance from the bridge down, is 23 meters. We know that the time initial is equal to 0 seconds. That's the time that the young man's feet leave the bridge, and that his initial velocity is also 0. We're going to take gravity as acceleration downward, so minus 9.8 meters per second squared. Part A asks us how long does the jump last. So let's take a look at, based on what we've got given, which expression to use. Let's try the expression that says the change in height, v final minus v initial, is equal to the initial velocity times time minus 1/2 gravity times the final time squared. Y final then is equal to minus 1/2 the gravity times time squared. Why? Because the initial velocity was 0, the initial height was 0, and the initial time was 0. So we've got a lot of initial functions here that are making the problem simplify, because when we multiply times 0, terms disappear. So hence every v initial term, or y initial term, time initial term, drives the entire problem to a very simplified time squared final is equal to minus 2 times the distance, y final, divided by gravity. So we just cleaned up this term here by moving things around. So again, if we take the square root of both sides of the relationship, we end up with the final time is equal to the square root of minus 2y final divided by gravity. Now we can start putting our values in. 2 times 23 meters, so there's our final 23 meters divided by 9.8 meters per second squared. We end up with, when we divide 9.8 into 46, 4.96 seconds squared, because our meters cancel out, or a total time of 2.17 seconds. So that's the amount of time it takes for the diver to travel 23 meters. Part B asks us then, how fast was the jumper traveling upon impact in the river? So if we use our expression that says the final velocity is equal to the initial velocity minus gravity times time, again, the expression simplifies. The v naught disappears because the initial velocity was 0. We end up with v final is equal to minus the gravity times time. We know gravity is minus 9.8 meters per second squared. We just solved for the time of flight, 2.17 seconds. So the final velocity when the diver hits the water is minus 21.23 meters per second. Okay, why negative? Because he's moving downward. Part C. If the speed of sound in air is 340 meters per second, how long after the jumper took off did a spectator on the bridge hear the splash? Okay, so we're adding a little different element in here by trying to determine what the speed of sound is and the amount of time it takes to hear that splash. So given 340 meters per second, again using our relationship that said velocity distance is equal to velocity times time, or velocity is equal to distance divided by time, we can move the terms around one more time, solving for the time that it takes for the sound to travel over the given distance x by the velocity. So we know that the distance the diver traveled was 23 meters, and that the speed of sound in this case is 340 meters per second. So we want to find out the time it takes to move that 23 meters based on the speed of sound. So the time for that distance is 0.068 seconds, which is approximately 0.07 seconds. So the change in time then, or the difference in time we're looking at, is the time for the speed of sound plus that of the time final. So the time it took for the sound to travel was 0.07 seconds. Add that to the 2.17 seconds it took for the diver to hit the water, 2.24 seconds after the diver hit the water, the sound traveled back up to the person on the bridge. Okay, so some problems here, has some interesting terms, a lot of mathematical manipulations that require, again, a little understanding from your algebra. I hope that helped. Thank you.